the coolest thing I have ever seen. Oh dear. Okay, hello everyone. My name's Joe Barnard. Welcome to the stream. We've been doing a lot of live streaming recently, and I promise it'll be worth it. I don't know. I mean, you're not really like paying anything, but it'll be worth it. Yes, my name's Joe Barnard. Welcome to the live stream. Today we're going to do some tuning and simulation on the Falcon Heavy model. This is one of the last steps that we have to take care of before we actually launch this thing. I've said it a couple of times, but this model is really, really hard to get off the ground. I mean, it's easy to get it off the ground. It's really, really hard to make it fly well. And so that's what we're focusing on today. There's a lot of tuning and simulation and a little bit of math that we have to do. Yeah, that's what we're going to cover. So let me just see what we've got going on in the chat here. Make sure we can hear me. That sounds good. Excuse me. A different stream time today. I definitely hear the complaints from everyone who is not in America when I stream at night, and they're very, very upset that I don't stream at friendly times to our European friends. So this is in an effort to try and make that a little bit better. Anyway, hello everyone. Hi David. Hi Colin. Thomas is here. Walt's Tomorrowland. I saw Parker put the lobster in the chat earlier. Hi Parker. Jared Bass. Joe Wakefield, Misty O, Teddy D, Lightspeed. We've got all sorts of people here. Grimmy, 9th 90, John, Gene, Lars Bressers, Jay, ya boy Sprinkles. All right, we've read up a couple of names. Let's get to work. Now we actually have a couple of things to do today. By the way, does anyone mind that there are a lot of live streams? I mentioned this in the last one. I don't want to keep this pace up necessarily. There's like a lot of work to do, and so I hope that's not something that people mind too much. What we're doing today is tuning the Falcon Heavy. So let's get started. There are a couple of videos on this channel already. I don't know if anyone wants to link to them on how I do the tuning process. Thank you, by the way, Thomas. That's very kind. The way that I do these tuning processes, it's something called a bifilar pendulum test. Now this is all like a multiple step process, so we have a lot to cover today. I also know that SpaceX is launching a rocket today. There's another rocket launch, and then there's maybe like a star hopper test, so we're gonna cut the stream off before those happen so we don't have to do which stream do you watch, that game. So I'm gonna write BPS.FH tuning. I didn't think too hard about going to the side of the page there. Is that backwards for everyone? Oh dear. Okay, it's backwards. Hold on, let me flip this really quick. I'm getting much better at OBS, but I'm not all the way there. So let me real quick flip horizontal. That's much better. This should be the right way. Yeah, there we go. Hi from India, and I appreciate your confidence. You really good. Thank you. Hi from India. Can I answer any questions before we get started? Does anyone have any questions? I should probably address what is this tuning process meant to do. We can probably use the Falcon Heavy second stage to illustrate this point. So This is the FHSS, which is the Falcon. Well, it's really FHUS. I like to refer to it as the upper stage rather than the second stage. It's pretty big. This whole model is very large. So most of these things are prepped for flight today. And before we actually hit that red button and get this thing off the ground, we have to understand how it's going to fly, how it's going to perform in flight. And that requires simulating a bunch of things. Now, with a quadcopter or something like that, if you have a PID controller, that's what I use to stabilize most of my rockets. If you have a PID controller on a quadcopter, you could toss the copter up in the air and just put random P, I, and D gains in there. Those are like the sensitivities of the system. You could just toss some random ones in there, guess it, and see how things go. And with a quadcopter, I mean, your chance of breaking things is kind of high, but it's not nearly as high as a rocket. And so you don't really have room to guess on rockets. You want to get all the math right that you can on the ground so that when it actually flies, you know, you're not picking up the pieces after the flight. So, yeah, that's what we're doing today. What we need to do is analyze how heavy this rocket is, how much force it's going to take to actually move it one direction or the other, you know, in all axes, and then we're going to bring it into a MATLAB and Simulink simulation and basically go through the process of tuning it. Now, this isn't going to be like the perfect way of doing it. In fact, this is not the correct way of doing it. It's a way that has worked for me, but if you are trying to actually build a rocket that goes to space, this is not going to work for you. And we'll get into that a little bit later. So you can see a MacBook in a MacBook in, oh, it's like MacBookception. Let me, wonder if I can turn down the brightness and you can like, just move it. This is probably a bad idea. Yeah, you can like see it go through the vortex there. The Mac keyboard was backwards. All right. Do you use counterweights for the cameras? Nico, good question. I do not. Most of the time, so these little cameras that I use are called RunCam 2s. I'll just pull this one off right here. And if I can demonstrate, well, let's just get the hard data here. They are very light. Let's see if we can zoom in. All right, how's that? Can you see that? You can see that. All right. So these cameras, I think they're exactly 50 grams. They might just be close to 50 grams. On the dot. Claws up for Joey B for guessing it right. These cameras are very lightweight, so using a counterweight or a counterbalance is not really necessary at the scale that I'm working at. Now, if you were working at a much smaller scale, like let's say an airframe and rocket masses that were half the size, this would start to become more and more of a factor. But the thing that is most concerning to me about cameras right now is aerodynamics. And so that's, if you put them on one side of the vehicle, let me move this over. If you put a camera on one side of the vehicle, like this, your vehicle is no longer symmetrical, right? Or symmetric. And so if you, let's see, if I put it here, it might make a little bit more sense. If you were to tilt the vehicle over in one direction or the other on this axis, and you're still traveling up, which means you have a small angle of attack, or AOA, there's going to be a roll torque that gets imparted on the vehicle from that camera. And if your vehicle doesn't have roll control, which most of my rockets do not, it's going to be trouble. That was a very long answer, but I hope that makes sense. My goodness, thank you for all the super chats. Robert, are we hitting the 7-hour mark of Charlie today? Yeah, Robert, did you join the Charlie Garcia live stream, the Charlie Garcia extravaganza? I don't know if any of you know. You should absolutely be subscribed to Charlie Garcia. I have promoted him on the community page a couple of times on the channel. But that aside, you should be subscribed to him. He's got a series on liquid rocket engines. The next one should be coming out soon. We did a massive live stream the other day, so we're not going for 7 hours, but we will go for a little while. And then Mriganka, I don't want to mispronounce your name, but I'm afraid I might be doing that. Mriganka, sir, how you started learning about aerospace besides having your college degree in music? When you started learning about it and how? I have some good details about that on a video that's called BPS.space update. and it's from the National Rocketry Conference. I put most of the process of like how I went about doing those things. The other video I might recommend is the books I recommend video that I just put up on the channel. Give those two a look. I discuss it a little bit more in there, but the process is a little bit too long for the live stream today. Okay, one more question, then we'll get started here. Can you watch the SpaceX launch with us together? No, thank you. Nothing against SpaceX, but that's more the job for Tim Dodd, the Everyday Astronaut, or channels that cover that type of thing. I focus mostly on the BPS.space program. Okay, so we're tuning the FH vehicle, and we need to know a couple of things about this rocket before we actually get it off the ground. I'll use the second stage as an example here, and I think we'll get started with that. Maybe we should get a better sense for like the whole rocket before we do that. Okay. Before we do this, let's talk about a few more specifics. I know I'm delaying things, but hang tight. It'll be worth it. We move this over here, and let's talk about changes. So one of the coolest things that will happen during the next flight of the Falcon Heavy model is we have active separation motors for the boosters. If you look up here, you'll see these tiny little A motors and a little igniter in them. And these A motors are going to fire based on mostly a timer and just a little bit other, some other control logic, but it's primarily based on a timer after launch. They fire, they push the motors back, or they push the boosters back and away from the vehicle. Man, it is crazy to me how it's crazy to me how hard it seems for some people to be nice in the chat today. Just be kind, man. It is so easy. So anyway, yeah, that's the main difference from the last flight. We've also got, we should have some more control authority on the center core because we had very little on the last flight. And then I pulled back some of the abort limits on the second stage. Most of the changes are actually pretty small. Okay, if we don't get started, we never will. Let me get the second stage back. And it also goes without saying, by the way, if you're going to be a jerk, I'm going to ban you from the channel forever. So, here we go. Starting off real strong here, folks. We need to know a couple of things in order to tune this second stage. We'll get started with the second stage, and then we'll move on from there. There's a video on this channel called Rocket Tuning, and I believe it has like the butt end of the Rocket Lab Electron that I built. It should be uploaded like almost a year ago or so. That sort of discusses the process in the context of this Signal flight computer from BPS. And so a lot of this, if you've seen that video, will be a recap, but we can still watch it if you want. So we need to know a couple of things. We're going to start off by needing to know can you see that? Is that like pretty much in focus? Yeah, it's good enough. We need to know the mass, M-A-S-S. We need to know the mass of the vehicle. We also need to know the distance from the center of mass. That is basically if you were to hold this rocket, where does it bounce, right? Where is it going to rotate about? You need to know the difference between the COM to TVC. So the center of mass to the thrust vector control mount. We need to know the distance. I'll explain these in just a bit. We need to know the distance from the COM to the string. If this doesn't make sense, that's okay. The string. Also, claws up in the chat for my awful handwriting. And then we need to know the distance from the, oh shoot, what is it? We need to know the length of the string. Length of string. Doesn't matter if it doesn't look good. The length of the string, we need to know, my gosh, what are the other criteria? I'm like totally blanking on most of these things. The time it takes for the vehicle to rotate, so I'm going to just put rot. And then finally, we need to know the thrust of the rocket, the AVG, or average thrust, and that's going to be in newtons. So all of these units here, mass is going to be in kilograms. They're all going to be in metric because I make sense and I don't use freedom units. Mass is going to be in kilograms. COM to TVC is going to be in meters. COM to string is going to be in meters. The length of the string is going to be in meters. The rotation time is going to be in seconds. And then the average thrust is going to be in newtons. Again, if this doesn't make sense, that's okay. We're going to walk through it. All right. Do I use a GPS system in my rocket? I do not. What other questions can I get? Sharpie on whiteboard. No, this isn't a whiteboard. This is paper. I got paper here. We're good. I have something on the whiteboard, but you can't see it yet. I love you for using metric. Thank you. All right. The mass of the vehicle is very easy to determine. I've got a scale somewhere here. Okay, hold on. Let me grab another piece of tape and just make sure I don't accidentally unplug one camera. I've come dangerously close to doing that several times now. There. That's better. Okay. We've got a scale. And I would like to put the rocket on it to see how heavy it is. But what I would actually like to do is put a stand on there first so I don't have to, so I can like balance the rocket on the scale. So make sure everything is out of the way. I'll zoom in a little bit and then we can read out what the scale is. So first I'll turn it on, zero it out. There we go, 0, and you probably can't really tell. Maybe you can, but it's in grams. And I don't really have a reference weight here, but you'll just have to trust me that it's in grams. And if I put the second stage on here, or the upper stage rather, rotate a little bit, we have 846 grams. So, 846. Everyone remember that number, 846. Here we go. Now, what did I say this was going to be in? Kilograms, right? So 846 is in grams. So if we go 0.846 kg, always put your units next to whatever number you write. Now the COM to TVC, once again, that's the distance between the center of mass and the thrust vector control mount. So if I bring the rocket over here, I want to mark a couple of things with a piece of blue tape. This video is sponsored by Blue Tape Incorporated. I'm going to pull a couple just tiny pieces of blue tape here, and we'll use them to mark different points in the rocket. So first, I'm going to lift the rocket up in different locations to try to find, like if I lift it up here, it's going to only come up on this side. If I lift it up here, we're looking for where it will balance, and that's our center of mass, sometimes also referred to as the center of gravity. Okay, so it feels like it's right about there. And I'm going to take a piece of tape, put it right there, and then I'm going to label it as CM. That's center of mass. And now, I'll just put a little dot in the middle so we can measure from exactly there. Oops, I got Sharpie on the rocket. Cancel the launch, everybody. All right, now that we have our CM, we can measure the distance between the CM and the TVC mount, or the thrust vector control mount. Now, oh, there's a fly. Did I get it? I don't think I did. Joey B got fruit flies, y'all. Okay, so there's a, just so we're all clear, there is an igniter in the motor, but it is not actually hooked up to the computer, so we are all good. Don't hook that stuff up until you're at the launch pad. So we've got a thrust vector control mount here, right? This is going to move back and forth, but the motor and where the exhaust comes out is not where we want to measure from, because what we want to do is measure from where the force actually meets the body of the airframe. That's where we're going to feel these rotational moments when we move the TVC mount around. And that's this set of screws right here. 1, 2, 3, and 4. So this set of screws is where we're going to measure to when we measure from the CM to the TVC mount. Now I've got a metric ruler right here. Actually, it's metric and imperial, but we're just going to use the metric side. And that's too zoomed in. Well, you'll just have to deal with this then. If I measure from the CM to the TVC mount, see if I can get this right. That's about the TVC mount. It looks like, in centimeters, we're sitting right around 17.5 centimeters from the TBC mount to the center of mass. So remember that number, 17.5 cm. But what did Joey B say about the units? Meters, right? So instead of 17.5, we'll do 0.175 meters. That's the distance between the COM to TBC. Okay, how am I doing? Is this interesting? People liking just measuring things and then writing it down? Next up, we have COM to string. This is an interesting measurement that I haven't explained yet. Should we take any more questions? What else is going on today? Anyone like going swimming or something fun? I don't know. I don't know what people do other than build rockets. All right. So the next thing up, as I mentioned, is COM to string. What does this mean? What it do be, right? Here's what it do be. In order to find what is called the mass moment of inertia, which is, you can think of it like it's a measurement of it's kind of a measurement of the angular force. Oh man, no matter what I say, I'm going to get it wrong, so you can just look it up. The mass moment of inertia is, if you don't want to look it up, kind of like how hard is it for us to rotate the vehicle one way or another. It's a measurement of that. There's a prize inside, by the way. I won't show you the prize yet. There is a prize, though. Okay. That's what we're going to measure here. Let's see if anyone else... Yeah, it's like the... Okay, Aaron O. Thank you. It's like the resistance to movement. Yeah, that's a great way to describe it. And it doesn't actually have to be rotational either, but we are going to be measuring... Got it! I got the fly. Oh, gosh, so satisfying. We're trying to measure the mass moment of inertia, and to do that, we can let this second stage hang on a pair of strings and sort of rotate back and forth like this, and using all of the things that we know, which is how forceful gravity is, how far apart these strings are, how heavy the vehicle is, we can find the mass moment of inertia of the vehicle, or at least a really, really close approximation of it. So that's what we're going to do now. And the first thing we need to do is make marks on the vehicle somewhere around the center of mass. So we need to make these marks of where we're going to be putting these strings. This process is not perfect, and as the disclaimer at the beginning of the video said, this is not... If you're going to actually go to space, this is not how you do it. You have a much more thorough analysis of the poles and zeros of your system, and you do a whole rigmarole. But for the Joey B miniature space program, BPS.space.com.gov, this is fine. So what I want to do is put 2 points equidistant from the CM, and I have them marked here. I believe I'll do like 20 centimeters from the CM. I think that's where we'll target. So if I put 20 right there, and I move this here, 20 cm ends up being like right there. And then I'm going to mark it. Make like a farmer and mark it. That's the worst thing I've ever said. It's the terrible joke. Okay, and then another 27 meters puts us right at the beginning of the curve of the fairing. So these are the hang points for the string. Just make sure I'm doing this correctly. That's 20. Yeah, that's about right. Okay. We have another hang point right there. I'll put a little marker. And now we're going to tie 2 strings around here. But before we do that, just to be thorough, we need to label how far apart we made these things. Also, is this in focus? Oh, it's really close. Yeah. Ladies and gentlemen, what did I say about units? It's 20 centimeters, but this has to be in meters. So it's going to be 0.2 m, or meters. All right. This is going better than I thought it would. Let's see. What else we have going on? So, Joey B, running out of ideas. We have all of these measurements here, and the next thing we have to do is the length of the string, and that happens once we actually hang this rocket from a pair of strings, which we haven't done yet. And that's because we have to put the strings on it. So let's get some here. Now ideally, you want to use really low resistance strings. So this is not perfect for the task. It'll be good enough, once again, good enough for Joey B, but not good enough for legit aerospace. I continue to mention the secret project coming up. There is a secret project coming up this fall, and this secret project will require much more thorough analysis. And if you're a patron of BPS.space, you already know what the secret project is, because it's in the BPS Discord. All right, there's my little plug. Plug over. Just make sure there's no roll torques in here. Oh, thank you, Russell. Sorry I'm late to the party. Russell, no sweat at all. Welcome. Welcome to the stream. So let's put these strings on, and then we'll hang this rocket. Now, on the top of the fairing, it's going to be hard for this to sort of stick around without sliding off. So I am going to put some pieces of tape on this just to secure it. And actually, you know what? So before we measure this, I'm going to take a guess as to what the mass moment of inertia on this rocket is. I'm going to take a guess, and then we're going to see how close I can get with it. Okay, hold on. Let me put this on. Does anyone have a guess? Wait, let's do this. Initially, so mass moment of inertia in kilograms per meter squared. That's the nominal measurement that you get. Does anyone have a guess for what the MMOI in kg per meter square is on this vehicle before we actually measure it? You have to guess. I'm going to go look at the actual number because it should be roughly the same. Oh, no, I don't even have it. Okay, never mind. The actual number is on a hard drive. Okay, hold on. Maybe I can find it. It's on a hard drive that's just unplugged right now. If I plug it in, let's see if I ruin everything. Okay, stand by. That's going to boot up real quick. A lot of guesses. None of them are right. Actually, no, some of them are close. It's not 42. It's not 27. It's not 4. Weatherworld, Mobiz, Linecraftman. All of you are quite close, or at least you are in the ballpark. You're in the ballpark. I am pretty sure, let's see. I think Weatherworld, you might be closest. You guessed 0.075 kg per meter squared. Yeah, you might be closest. I think it's a little larger than that, but you're probably closest. Hey, it's Tom Stanton! What up, Tom? Welcome, dude. It's good to see you. Well, I'm not, I can't see you, but you know what I mean. All right, let me see what the actual MMOI is. The drive should be plugged in. They should be booting up. They're kind of doing that, but not really. Okay, stand by. Okay, hold on. I have to do this. I'm sorry. The screen quality is going to suffer. But it will be worth it for science. I have to know what the actual measurement is. So on drive 23, if I unplug it and then I plug it in up top here, it'll be worth it, I promise. I don't care if we lose viewers. You can leave if you want, but you'll never find out the answer. Okay. Stand by. Who's calling? Oh, okay, hold on. Oh boy. Hold on, folks. I have to go to a really quick intermission. I'll be back within 30 seconds. Hi, pals. I'm back. Joey B back. Had to take a call. Real quick, though, I have here the data. This is an incredible sidetrack. The test data from the original Falcon Heavy model launch back in November. So if I look under tuning and simulations, I can find what the actual MMOI is for the upper stage. So... okay. All right. I have it here. Put your guesses in the chat. Put your guesses in the chat, and we will see what it is. I'm going to go back to the workbench. Oh, thank you. Oh, man, I am so sorry. I am probably going to butcher your name. Guillaume Humbert. Man, I know, because we've chatted before. I just don't know how to pronounce your name. Hi, Joe. Good luck. Good luck on your upcoming flight. When can we destroy your email inbox again? Not soon. I will tell you that. I regret that deeply. Okay. So, I'm looking at the answers. Someone is really close. There's one person who's very close. Ooh, okay, there's one person who's also pretty close. Someone's doing math. I can tell. Someone in here is doing math. They're figuring it out. Or they just got really lucky. All right, here's the answer. First of all, the closest person so far, at least that I can see right now, is Electrogen with 0.017 kilograms per meter squared. Because the actual answer for the last FH upper stage is 0.016. Very, very close. And it was 0.0165. So let me just make sure I read that correctly. Yeah, 0.0165, which means if you round up, you got it exactly. That's what it was. So the last time was 0.0165. We're just going to leave that in the upper corner. And now it's time to actually test. All right. Should we do one or two questions? We should do one or two questions. Let's do some questions. Ask me a question. And I will do my best to answer. And then we will test. Will you introduce horizontal control during ascent? Gustav, great question. No, I will not. Not for this flight, at least. But for the secret project, yes. That's what I can tell you. Do I use Linux anywhere? I used to use Linux for a little bit for like some stuff, like years and years ago. But I just like Mac better right now. I like the way the interface looks. You should join the OLF podcast. Man, that would be cool, but I also have zero time ever for anything at all, ever. so I'm not sure I could permanently join. I would be happy to be a guest, though. Hi, mate. Show us your Simulink model, please. Later in the stream. Yes. Which IMU is on the current signal? I am sorry, that is not currently disclosed information. Sorry to disappoint. But you can see the IMUs on all of the past computers on BPS.space/avionics. Okay, let me try to do like 2 more. Will the launch and land rocket have fins? Yes, it will, but they will deploy. They'll fold out from the top of the vehicle. So for ascent, the fins will be sort of stored, and then they'll fold out. They'll also be flat. I showed a video where they were sort of rolled around the airframe, and they'll be flat. So the top of the vehicle will look a little bit like a rectangular prism, or like a elongated cube. And let's see, one more here. What integration method you used except one-step Euler? Maybe Runga-Kutta. Yeah, I don't use Runga-Kutta, but that's I think it's objectively the better integration method. I do just like step by step. It's really nothing fancy. And again, for like future models, methods like Runga-Kutta and just more better methods are going to be required. Hi, Trista. Thank you so much. Hello, Joey B. Boneless or traditional wings? Boneless, but I feel bad about having that opinion. I like boneless better, but I feel bad about having that opinion. I feel like traditional is better. Joe, could you wiggle the gimbal on the upper stage to help with extra thrust? Yeah, but the upper stage already is so unstable that I just don't want to mess with it too much. So right now, this bad boy, I can't guarantee it, but it's probably going to become unstable near the end of the flight. It ends up going up to like 65 miles per hour or like 30 meters per second, which with such an unstable build, you could put fins on it. That could help a little bit, but I don't know. We're just going to send it, and we might feel the consequences of sending it, if you know what I mean. So the next thing is the length of the string, and we need to actually hang it for that to be a thing that we can measure. So let me switch views, and we will hang the rocket and start to test for its mass moment of inertia using something called a bifilar pendulum test. I'll say that one more time if someone wants to put it in the chat so you can help spell it. It's a bifilar pendulum test. If you look up bifilar pendulum test NASA, there's a great video of them texting. It's the X30 something. They use the same method to test the NMOI on one of their aircraft. Okay, here we go. To the next view. New view, new me. Actually, hold on, I need to stand. I did set up for this stream, but I didn't do a very good job. So, hold on here. Let me move my laptop so I can still see chat. Okay, can everyone still see and hear me? Are we all good? Oh, I'm not live. There we go. Let's see how this sounds. There we go. Let's see how this sounds. Yeah, so it's not great. It's all right. It's a little bit more echoey, but we should be okay. Now, you can also see down here, you can see my hand in the viewfinder there. We're going to be hanging the rocket from the edge of this table. So why don't I go ahead and move things around here. Put a couple little rocket cradles at the bottom. So there we go, 1 and 2. Whoop, don't fall off. And then we'll bring this guy down here. And the extra string up here. Now I mentioned earlier that I have some marks on the table that one of the things that, how do I explain this? On our sheet here, where did I put the Sharpie? Oh boy. This is a disaster. This is the worst thing that's ever happened to me. There it is. I mentioned earlier that we needed to be precise about our measurements between the hang points here, which are basically that's what the filar is in the word bifilar pendulum test. We measure them at 0.2 meters apart, or at least each of them is 0.2 meters away from the center of mass. And so we also have to hang them 0.2 meters, or I guess a total of 0.4 meters apart at the top. So that's what we're going to do now. And I have this piece of tape here. Let me re-emphasize the, there we go. Re-emphasize that, and then right here, this is the center point. This table used to be like a nice kitchen table to like have a nice dinner at, and now it's just covered in tape and pockmarks and rocket propellant. Thank you, Alexander. Thanks for the super chat. When will I launch? I cannot actually tell you that. So one of the weird things about BPS gaining popularity, by the way, hold on, let me check one thing. Let's see. Stand by. I have a thing to check here. Wow! It happened! So the channel trailer just passed 1 million views. That's the first video I've ever had that passed 1 million views. That's insane! That is unbelievable. Claws up. Dang. One of the weird things that has happened as a result of BPS gaining popularity is I start to get more concerned about like what info I publish about where I am and where I test. So I've said it a couple of times where I test. Please don't put it in the chat. But I really like to test with no one else there. And it's not because the test fails and I like fake it or something. It's because it lets me stay a lot more focused. If you saw the video on the books that I recommend, one of the things that the Wright brothers did was the same exact methodology, where it's don't invite people to the test, don't make a big deal about it, just keep it nice and private. So I have a couple people coming. We do have a launch date scheduled, I just can't disclose when it is right now. And at some point, you'll just see the video pop up and it'll be like, oh, well, it launched. Or if you're following on Twitter, I'll probably give you much more updates. He says use metric, but goes 65 miles per hour, not kilometers per hour. I put meters per second in there, too. Thank you, Alexander. All right. So, yes, the test date is very soon, though. It's certainly within a week, and that's what I can tell you. So, as long as things go, well enough that it like warrants a full video and explanation, like if the rocket like, I don't know, just doesn't ignite on the pad or something that just doesn't warrant a video. I don't know. You all know how this works. The video will be up soon. So we need to test this stuff. I've been moving extremely slowly through this process. I've got a couple of clamps here. Move this around. And then what we're going to do is lift the rocket just slightly off the ground. This is harder to do with a bunch of cameras around. I usually don't have a bunch of cameras here. So when I pull this string, the rocket's going to come off the ground just a little bit. I'm going to make sure it's right at that point, 20 centimeters from the CM. Oh, actually, wait. I have a better idea of how to do this. We can use... Yeah, this is way better. Let me move this. Okay. So I just want to hang it as kind of accurately as I possibly can. Now I'm going to clamp this down. And it's kind of hard to do without messing things up. Okay, that didn't really work. That's pretty good. That's good enough. It'll work. And then we have to do the other side. Sorry if the audio is a little bit messed up. So this side, we're going to hang it here. Oh, see, now it's swinging. He's swinging. And clamped. Now the last thing that I want to do here is just look on the ground to see... Okay, so I need to raise this side up. We want it to be kind of like both sides need to be equidistant to the ground. So I'm going to raise that. The more accurate you can be about this, the better your test results will be. And the more accurate your test results will be. Okay. that looks pretty good to me. So now, I'll move the clamps. Someone's saying stuff in the Discord. What's going on here? I need to change the chat mode too. Oh, we have 400 people. Thank you all for joining, by the way. If you're just joining, we're about to test the mass moment of inertia on the FH second stage. So the next step here is to measure, a little brain fart there. The next step here is to measure the distance of these strings. You can see it pretty well. Yeah, it's not perfect, but you can see it pretty well. We need to measure the distance of these strings roughly from where they are attached or where they come off the table to slightly below, like slightly into the airframe. I found that to be the most accurate point to measure from. We're going to do this in centimeters and then convert it to meters. So right now, to me, this looks to be about 55-ish centimeters. Say like 55. Yeah, like 55 cm. And if I come over here, it's not 55 cm. Oh, no, it's about the same. Okay. So on our string length, let's see if someone can see this. On the length of string, how do I do this? We're going to go O.55 meters. The handwriting is getting progressively worse. Okay, the next part is one of the parts that I'm pretty sure, when most people have failures with their signal kit, this is where they mess up. I'm pretty sure this is where it happens. It's very hard to tell, because most people don't super thoroughly document their process. That's all right, they don't have to. So we have to time the average rotation period. Basically, it's going to oscillate in a sort of sinusoidal motion, right? And so we have to time each full sine wave. Oh my gosh. We have to time each full sine wave. I am so losing my focus here. Had a lot of coffee this morning. Okay. So the way that we have to do this, first we don't want to, it's very hard for a second stage like this. One of the things that's going to be an obvious influence here is the camera on there. The camera is going to change the MMOI on the different axes. And the thing that we want to try to do is keep the CM pretty much still. You'll see this in the tuning video that I put up about a year ago as well. But the CM needs to stay just about still. And then if we start to rotate like this, if we give it a torque, a rotational torque, oh, see, that wasn't very good. If I do like that, yeah, see the CM moves just a little bit, but that's kind of the oscillation that we want. That's a little bit strong for what we want, really, but I'll let it sort of damp out, and then we'll start to time it. Let me turn off notifications here, because I feel like I'm going to get in trouble for that if I don't. Okay, hold on, stand by. We're going to get a timer out. And how does this look? Can you see the timer if I put it here? Yeah, you definitely can. Maybe I'll move it back a little further, like there, so you can see the vehicle too. Yep, you can still see that. Okay, great. This is good. And actually, because this is probably upright for you, that's probably the better way to do it. So what we're going to do is we're going to measure 10 rotations. Do I watch Mark Roper? Of course I watch Mark Roper. Mark Roper's awesome. So we need to time the average rotation period, which is when it goes to this way, and then this way, and then back. So that's a full period, right? We have, if the rotation starts here, we measure from here to here. Does that make sense to everyone? I'm trying to make sure that everyone's sort of on the same page about like what's actually going on. So here we go. I'm going to give it a little rotational torque here. We're going to try to make sure we're still moving around the CM roughly. That's a pretty good rotation. I'm going to come over here, and then I'm going to pick a point. So we'll pick the point where this goes in this direction as one of the peaks of our like little sinusoidal motion here. And then I'll start the timer from one of those. It'll go from 0 to 1, and then from 1 to 10. It'll make sense in a second. I'm doing a bad job explaining this, but let's go ahead, start the rotation, and here we go. And peak. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So what did we just do? 25-year-old man rolls a rocket on 2 different strings and times it. There's your headline. What did we just do? We timed how long it took for the rocket to oscillate back and forth over the course of 10 oscillations. And even though we don't actually need all 10 of those oscillations, if you time it over a period of 10 seconds, or rather 10 oscillations, and then you divide by 10, you get a really accurate measurement of the average period. So if I divide what we got, which is 11.31 seconds, if we divide that by 10, you get an average rotation time of 1.131 seconds. All right, so that's our average rotation time, and then we just need our average thrust now, which is about 15 newtons, because this one's flying on an F-15 right now. That's at least what the upper stage flies on. So I'll put 15 newtons, and there we go. Now, here's some special sauce that I cannot fully explain. We will do the Simulink modeling in just a second, but I want to show off. Joey B has to flex. So get ready, because I gotta flex. I have no choice but to flex. I'm so sorry. Here we go. We're going to turn the rocket on. There it is. Signal. And now it doesn't need to be on anymore. I have to flex. I have no choice. So can you see the screen? You can't really see it. Let's turn down the brightness. Okay, can you see that? Kind of. Not really, though. Okay, you know what I can do? Let's switch views. Ba-ba-ba. There we go. Back to this view. Signal R2. Can you see that? That should be easy to see, right? Yeah, there we go. Nice. We got a little scrolling shutter there, but should be all right. Should be permissible. Let me move the mic so it's a little bit louder. All right, everything still look good to people? So this is the Signal R2 app, which you can use with the Signal R2 TVC system. I will mention it's not for sale right now. We might do a small round of sales in the fall. And then who knows what happens. There's some upgrades I'd like to make after that maybe. But that's the current state of thing. So what I'm going to do is I'm going to flex. I don't flex often, but it's going to happen. Drop a like for the flex, please. I spent so much time last summer doing a bunch of math. My buddy Johnny, actually, who works with Veritasium now, but my buddy Johnny helped me with a lot of it. Doing so much math and trying to devise, I can't talk too much about it, but to devise some special sauce so that when you input all of these values here, your rocket's mass, your COM to TVC, your string length, your string COM, your average rotation, your average thrust, there's easy math that you can do. We can look at it later if you guys want, but there's easy math that you can do to get to the mass moment of inertia. That's the MMOI of the vehicle. That's what we're looking for here, and it's what will pop into our Simulink simulation to actually actively tune our vehicle. But most people don't have access to aerospace grade software like MATLAB and Simulink. So what do you do if you're selling a consumer product? Well, you spend 1 billion hours developing your own secret sauce of how you go from inertia and all of these values to the optimal PID gain, and putting it into an iPhone and Android app. So here we go. Let's put these values in and see what it comes up with. If I go to... Now, it's going to be really hard. It actually might yell at us for the second stage because it's such a small COM. There are safety limits in here too. So as I think about it now, we're probably going to get yelled at by the app. But let's try it. So mass in kilograms is going to be... Boy, it's really hard to see this. There's not much I can do, though. Sorry for the quality. It's going to be 0.846 kilograms. We did that before, right in here. Maybe if I turn it up a little bit, it should be helpful. Let's see if that makes a difference. Nope, that's worse. That's so much worse. Is that better? That's a little better. Let's go down. Okay, nope, I made it worse. I'm so sorry, everyone. Now the COM to TBC distance, does anyone remember that? That is 0.175 meters, so 0.175 meters. The string length was 0.55 meters, 0.55. The string to COM distance was 0.2 meters. The average rotation time was 1.131 seconds. And the average thrust was 15 newtons. So these are all of our values here. You'll see I'm not a pro app developer. I did the best that I could, but there's stuff like you can't see what you're typing when you're on the bottom. I know there are ways to fix it, but you know, it's a lot to do. Now, I'm going to take a quick screenshot just so I can remember this stuff. I also have a whole page of like helpful things under the question mark for like, what do I do? Here's how you do these things. But when I hit tune, it's going to do a bunch of math and it's going to figure out the right PID gains. But as I mentioned earlier, I think it's going to yell at us. Pretty sure it's going to yell at us. Yep, here we go. COM to TBC distance is out of safety boundaries, too low. So it doesn't like that we've put our COM and TBC so close together because it means the vehicle is going to be very hard to control. Just for the sake of basically jacking things up here, let's go to 0.2. I think that's maybe where the limit is. Yeah, okay, so it'll tune if I go to 0.2, so that would be 20 centimeters instead of 17. So in here, we have our tuning results, which is 0.019. So we have increased slightly in mass moment of inertia. For those who remembered, we were previously, during the previous flight, at 0.016. Electrogen guessed really, really close at 0.017. And now, and now we have 0.019. So that is the current result. Okay, hold on 1 second here. Yeah, that is the current result. So with these results, the app has taken in all of this information and it has generated a bunch of PID values for us. So the P should be 0.08, the I should be 0.157, the D should be 0.035, and so everyone saw the pizza party. Anyway, yeah, so this is all the information on what the PID value should be. Now, if I try to send them to Signal, they won't actually go to Signal because we've turned off the flight computer, and now I've lost these PID gains for good. They're gone to the wind. All right, so we don't actually need this. If I go to tune again, I'm going to take a screenshot of these values that were generated, and now we can bring these all into a Simulink simulation, and this is basically how we tune the rocket for flight. Especially, we couldn't use the accurate COM to TBC values right here, which were 0.017. So I'm going to manually bring it into Simulink, build a simulation that should show us how the vehicle would perform during flight. And yeah, the other thing, just to give you a quick heads up, this is not a visual simulation. Like, you're not going to see a 3D render of the vehicle. What we're going to be looking at is plots, like a little line that goes up and down and curves like that. And so that's just what we're looking at right now. It's not, you're not going to see like a very pretty animation of it because that's not the information we're looking for. Now, here we go. I have to go to a quick intermission because I drank way too much water and I have to go to the bathroom. So please visit the website that shows up on your screen and don't go away because there's lots more cool math to come. Don't go away. Ever. All right. Hi, everyone. Welcome back to Joey B's live stream extravaganza. Okay. So, thanks for waiting. Sometimes MATLAB takes a little while to start up, but I'm at the computer. You can see the parts for the FH in the background. I'm at the computer, and it's time to do some flight simulation for the Falcon Heavy. We're just gonna do a really, really basic simulation. The actual one that I use is kind of far more complicated, but I feel like it's better if we build things from the ground up and actually get a sense for what's going on in these simulations and how these things get done, at least for me. Once again, I will state this is not the complete proper way to do this. There are a lot of books that I'm reading right now. I don't know where they went. I think they're in my room, but a lot of books that I'm reading right now, and I'm trying to find the accurate poles and zeros of the system and what the optimum control is. And this is mostly a experimental and almost visual approach to it. So here we go. This is my desktop. By the way, this desktop is from Brady Keniston, who is one of the best photographers that I know. He's a launch photographer. This is from Falcon Heavy STP2. It's an engine shot. It's awesome. This isn't the full desktop because I've got all the OBS stuff and broadcasting things on my right here. But I guess that's your, on your right, on my, whatever, it doesn't matter. Excuse me. So let me just go back. Okay, there we go. I didn't do the jump scare. I'm sorry, everyone. I should have done the jump scare. So the first thing we're going to do is we're going to get a window up here. This is a Simulink window. This is sort of what this looks like. It's a blank canvas right now. We've got nothing on here. So let's take a look at what we've got going on. Is everyone here familiar with what a block diagram is? A block diagram is a representation, at least in our case, it's a representation of a system. That's a really general way to put it, but that's kind of what it is. It's a representation of a system. And so what we are representing here is the way that the Falcon Heavy upper stage model is going to behave when you put given forces or anything against it. All right. So what am I looking at here? There's a lot of questions I don't understand. Now that's a wallpaper. Okay. So in each block diagram, you have, let's just do a quick demo here. I want to make sure that everyone can see this pretty cleanly. But if I click, let's see, let's add a constant. A constant is just a constant number that when it comes out of the block diagram, oh boy, Simulink, we can set our value for the constant. It should prompt us for that. There we go. Okay, let's say a constant value of 20. This doesn't have to be in any specific units or anything like that, but we have some constant value of 20, and then we do another constant down here, and it's a constant value of 5. And then we could put another block in our diagram right here. We could say sum. We could sum these two things together with the two signs plus and also plus. So there we go. These two things are going to sum together. And if we put 20 and 5 into there, and then we put a scope, which is going to plot our output, the scope with one input port should show 25, right? So if I open up the scope here, I think it's having trouble because OBS is running. Huh, that's interesting. Why don't we see a value of 25 on our y-axis here? That's really interesting. Well, it's because we haven't run our simulation, right? So if I click the play button here, or if I click the play button here, it's going to run for 10 seconds. So let me go ahead, get back to the scope. I'll click the play button here, and we should have a value of 25 in our scope. Here we go. It's going to take a second to run. And 25! Claws up, everyone. Now, this is about as basic as it could possibly get. MATLAB can get way more complicated than this. It's really good at matrix math. It's really good at a bunch of different things. But this is just sort of a demonstration to get everyone up to speed of what a block diagram is and what we can expect from it. Let's just get a little bit more familiar here. Let's say we didn't want to immediately have the 20 and the 5 summed together. So let's move a couple of things around here. Let's say we wanted the 5 to be added to this 20 a couple seconds into the simulation. I hope this is interesting to folks. My dad works at MATLAB, right? Jared, he works at the MathWorks, which makes MATLAB. So yes, you're correct. Let's say that I wanted to add these two together, but at a certain time step. So let's do a time-based simulation. We'll put a small switch in here. This is not necessarily the most efficient way to do a simulation. But with a threshold of 1, we'll have a small switch. And you can sort of guess by this current diagram in here what's going to happen on this switch. So we have some nominal input here. Let's say 20. We'll switch the 20 and the 5. We have some nominal input of 20. And when the input, which is going to be right here, we'll put another constant of 1. When the input is greater than 1, we're going to switch to actually send the 5 through instead of the 20, right? So maybe we'll edit this to 25. I promise, I know this is boring to start with. I just want to bring everyone up to speed here. So we've got this constant of 1, but it's always going to be on, right? We don't want this to always be 1 because we want our simulation to be timed. Well, I can do this in a couple of ways. I'll do it in a really janky way right now, where I will add a delay into our simulation. So this block represents a delay in whatever signal comes into it. It'll delay the signal and then push it back out. So if I go into the delay block and I set it as a value, we have to set our sample time correctly. So like our sample time could be 100 milliseconds, and we have a delay of 15. That means that for 1.5 seconds, I'm moving a little fast if you're unfamiliar with this stuff, but for 1.5 seconds, this 1 is not going to pass through here. Now, does anyone see a problem with this already? Let's see if anyone can catch my problem. I'll go ahead and hook the scope up, but before we run it, there's a problem here. Something won't work about this, and I want to see if someone can catch what won't work. It shouldn't be actually that hard to figure out. Let's see. I'm going to go ahead and save my model too. The 10-second runtime is not the problem. Nope, the 20 is not the problem. Yep, okay, Russell King gets it, greater than, not equal to. That is right. So our switch is set to be when the input is greater than 1, then we switch. But, ladies and gentlemen, the input is 1. So we have two ways we could fix this. We could make the input 2, and that would certainly work. Or, if we didn't want to make the input 2, we could go into the switch block and then edit the logic in here. So criteria for passing first input should be greater than or equal to the threshold. So we'll choose that. I'll open up the scope, and let's run the simulation and see if it works. So we should see at 1.5 seconds, we move from a value of 20 to 25. So here we go. There we go. It scales it so it looks a little bit weird, but we've got a 20 down here and a 25 up here. Let me grab my laptop really quick and make sure this stuff is coming through. Okay, yeah, that looks pretty good. Drop a like if you love the number 25. Okay, how are we doing? Is everyone following along? I know this is very simple to just get started. But I just want to make sure everyone's following along, and then we'll get rolling here. Do I program MATLAB? You can. You can. Can't tell what I can say. You can do really advanced things in MATLAB. You can also use something like MATLAB Coder to actually generate C code for you. So you don't actually have to. I mean, it's really helpful, and you should, because like you might have to edit it. But MATLAB Coder could generate C code for something like this. If I go into code, I don't actually use this feature, so I'm not super familiar with it. But yeah, so Code Generator Advisor, and you could build the model. There's actually an Arduino starter kit for this too. I looked into doing this for a while. They have, if you go into the block library, for you can do like PWM controllers, I think. Search. Yeah, you could build your whole flight software in Simulink, and then actually have it generate the code for you. Okay, no results for PWM. It's probably Pulse then. Yeah, so Pulse generator. I don't think I have the... Anyway, but there's an aerospace block set, so let's look at that. So you can simulate a linear second order actuator. So this would be like if you have an LTI system, or if you're representing as a completely linear model. You could do a nonlinear actuator, so that's like when your input is not directly a function of your output is not directly a function of your input. I know this is a lot. Sorry for those who are not. These are things that simulate aerodynamic models. So it's pretty easy. If you're using something like Simscape, that's a visual simulator of what's going on. You could use one of the animation blocks. Equations and motions, we're going to be using the 3DOF block here. GNC stuff, so there's all sorts of things. There's like, yeah, it's pretty cool. There's a lot of good stuff in Simulink. You can see why it's used in the industry. Okay, Joe, can you please slow down? Yes, I can. I'm so sorry. I get excited about these things. All right, so let's ditch these. We're gonna get rid of them. Say goodbye. I hope you didn't want them because they're gone now. And let's put a new block in here. This block is going to become called From Workspace. The From Workspace block pulls from our MATLAB workspace, which should be predictable. But in my MATLAB workspace, which is the main MATLAB window that's not shown here, I've got a model, or I've got a, it is a, what do you call it? Oh my gosh. A spreadsheet. It's a spreadsheet. It's a spreadsheet of the F-15 rocket motor, F-15_TC, I believe that's correct. And so if I scope that real quick, just one, that's fine. And if we look in here over the course of, let's say, like 5 seconds instead of 10, if we look in our scope, we should see the thrust curve of an F-15 because that's coming from our MATLAB workspace. So if I click play, that's not right. Oh, wait. That's super weird. Why does it go down like that? Hold on. It shouldn't go down after there. I must have like some weird value in there. What if I simulate for like 20 seconds? Does it ever stop? Maybe I have to put 2 zeros in here. So let me do this really quick. Uh-oh. Don't freeze. Don't freeze, MATLAB. Don't do this to me. Oh, jeez. Oh my gosh. Can we get an F in the chat, please? I pushed too hard. I flew too close to the sun. Force quit. All right. We're going to go back, but please put an F in the chat while I try to reboot MATLAB, and we'll get going again here. Please put the Fs in the chat. All right. Stand by while I reopen the sim. All right. Just MATLAB things. It crashes every now and then. I also really need to like update my computer, or not update, but reset. My computer is in dire need of a full reset here. All right. Now, if I start a new Simulink simulation, let me open this again. And open this workspace. Stand by, everyone. We're getting there. Don't go away. We can do this. It just takes a little while. And OBS really does not love working with MATLAB. You should upgrade from the trash can Mac. Jared, I should upgrade from the trash can Mac. If you would like to Venmo me $10 to upgrade. No, I'm kidding. Don't do that. All right, it's still starting up. Can we do some questions here? Let's do some questions. What can I answer for everyone right now? What are we all doing today? All right. Let me go to live chat so I can see what's going on. All right. Why does my neck hurt? I don't know, man. Maybe you slept on it wrong. Any tips for model rocketry? That's so general. I don't really know. When are you doing fuzzy control? I don't have a huge interest in doing that stuff. Does your simulation factor in the COM shift after the fuel is burnt? No, it doesn't. It's not actually a crazy big change. Like, it's smaller than you think. Okay. Let's just leave this. Ignore. Sorry, our thing is starting up again here. Finish. Ignore. Stand by, everyone. How fast do your rockets go? I usually try to keep them under 20 meters per second. Is there a Hot Wheels Roadster payload? Yes, there is. Yes, indeed. There definitely is. All right, here we go. We back, everyone. We're back with our old simulation. So let's get to where we were before, which is we had a from workspace block. Okay, I'm going to save the model one more time. And boy, yeah, it's not usually this slow. OBS is messing things up. All right, so the from workspace block, we're going to pull the F15 TC. It's going to prompt us. There we go, F15 TC, which stands for thrust curve. And the F15 TC, that's just going to be the signal for the thrust curve of the motor. We have to do a couple of things to this. We're going to try to build a model of how this thing works. So let's get the 3DOF block. This is sort of an equations of motions thing. And I'm not really going to explain all of the stuff that we have going on here. You'll just have to sort of trust me that it works. So we're basically simulating just one axis of rotation, and if we want, we could do some translation stuff in here too. But we have all of these inputs and all of these outputs. Now, if we wanted to simulate the flight of the rocket, we could put the F-15 TC into the Z-axis, the Z-body axis, and then we could do something like this. In our block parameters, we could set the initial mass to like, yeah, okay, this will be 1 kilogram of initial mass. Our initial velocity is 0. And then you can set initial conditions for all of these types of things. Our acceleration due to gravity is going to be negative 9.81. And then if we go and bring a scope up here with just one input port, and then we pull out of our X and Z axes, I know this might look like just nonsense to some people. If I hit play, we should have a simulation of flight with an F-15. There we go. All right. Oh, our simulation is way too long. Let's simulate for like 5 seconds. Hang on. It just scaled like way down because we let it go for too long. We don't have like lower limits. Here we go. Oh, come on, buddy. You can do it. Oh, no. Don't do this. Where's the gif of Michael Scott going, "No, God, please, no"? No! Why? I think it's OBS. I'm blaming OBS. All right. All right. This is ridiculous. This shouldn't... All right, we're going to try this one more time. You just have to be patient. Oh my gosh. All right. Force quit. Where's the force quit? We're going to force quit. Let's answer some more questions here while I reboot one more time. And if it doesn't work the third time, we're just going to find out something else to do. Maybe we'll look inside the fairing and see what's going on. But I'm going to reboot MATLAB. We're going to try this again. Oh, jeez. Oh, boy. What can we do for questions here? Isn't there a SpaceX launch tonight? Yes, there might be two. There's definitely CRS-18, and I believe there's a Starhopper launch as well. Why do you not use OpenRocket? Because OpenRocket cannot simulate all of the things that I want. And I want more control over my simulation than OpenRocket allows. Okay, finish importing these things. And once it does that... Hey Joe, what are your incentives to keep you on the ball with testing rockets? Thanks from Austria. Wow. What do you mean exactly? If you mean like what keeps me motivated about stuff, it's just focusing on things that I know I can do well at. I know that sounds weird at first, but if you are always doing hard things, you're always going to be running into walls. I'm not good at explaining this, but it's focusing on the little wins. That helps keep me motivated. We're still restarting here, by the way. Don't go away. Doing my best. We're losing viewers, but nothing I can do. From which stream are the crabs? I do not remember which stream they came from. Hey Joe, just started watching the stream. We are tuning, what are we doing? We're tuning the Falcon Heavy upper stage. We're trying to, at least, and this is turning into more of a tutorial. Although, to be frank, it's now turning into more of an exercise in patience, as MATLAB has crashed twice now. If it crashes a third time, we're going to have to find something else to do, because this is untenable. OBS is sucking up a bunch of computational power. So here we go. 1 second here. And let me transition over. Okay, we've got our Simulink model again. Let's try this. I'm just going to save it. I've unplugged a hard drive. Sometimes the hard drive messes things up. So like if we're just going from the root drive, it should help. So let's give this another shot. I'm feeling confident. Let's get the From Workspace block again. There's another fly. Oh, it's hard to get them. And then from this From Workspace block, we've got the F15 TC. And I'm just going to skip a couple of steps because we've covered this before. Next thing we need is the 3DOF block, body axis. I'm just trying to show that we can use this. This is our force, newtons, into the 3DOF block with an initial velocity of 0, with acceleration due to gravity of negative 9.81, an initial mass of 1 kilogram. And we can use a scope at the very end of it with one input port right here. I'm going to save. And then we're going to plot. All right. Okay, here we go. Fingers crossed. It should just simulate the flight. Yes! My goodness, thank you. So if we had a mass of 1 kilogram with an F-15 rocket motor, and this is in no way real, but if we had a mass of 1 kilogram with an F-15 rocket motor, we would ascend to roughly 35 meters. Does anyone know what's wrong with this right now? There's a lot that's wrong with this, but go ahead and tell me what's wrong with this. There are things which are wrong. Put it in the chat, please. Let's get some error checking here. We'll do that. Actually, let's do a new scope. Scope with 2 input ports. There we go. Yeah, okay, everyone's got it. No aerodynamic force, no crabs there. Yeah, right, so this is assuming that we have no drag in our rocket, right? And let's just take a look at another scope here, which is going to plot velocity and acceleration. So here we have our velocity. Let me use the zoom tool and oh dear. Okay, hold on. Let's zoom back out. Let's use the zoom tool and look at our velocity and acceleration. So the green line, this more rigid one, is the acceleration of the rocket. You can see it basically mimics the thrust curve. We don't have any thrust losses programmed into here. There's actually a lot going on that we don't account for. But we start going up. We also have this like weird discrepancy at the bottom here. Oh my gosh, no. This is the worst thing that's ever happened to me. Never, ever, ever again will I do MATLAB on a live stream. Okay, here's what I can tell you. It so obviously doesn't do this every time, because otherwise I'd never get anything done. So something happens between OBS and MATLAB where they just like fight. They just fight each other in the computer. I can't believe it crashed. At least I can show you. The green line is the acceleration of the vehicle. The blue line is the velocity in meters per second. So we would hit about 15 meters per second. I can't believe it crashed a third time. All right. Well, we have to still do something because I'm here, right? I'm here. I'm hanging out. Here's what I can tell you. Usually what you would do in MATLAB is at least what I do, is I end up sending the F15TC through a vector resolution section where you convert to radians, you send it through sine, you multiply by the angle of the TVC mount. This is a whole closed loop thing that I usually have. You put it into the moment thing of here, you program the inertia in correctly. If you want, you can program in a ramp of inertia change while you lose mass. And then you can plot it. You can also take the output of theta, which is in radians. That's going to be your orientation. That gets turned back into degrees. You feed that back into the PID controller, which you can just generate a PID here. It's a feed forward, or it's like a forward Euler or something like that, whatever it is. Back into the PID, you can tune the PID. You can even open the PID tuner. And then after the PID, you simulate either through a transfer function or through like a janky moving average, like delay thing. If you don't want to linearize it, you can feed that through that to simulate the slosh and the slop and the TVC mount. You can do whatever you want, and then you send it back in to the vector resolution here for the thrust curve and TVC block. That's how this works. Oh boy. People want KSP. I'd be down for KSP. Simulate it in KSP? Should we do that? Are people into simulating the model Falcon Heavy and Kerbal Space Program? Here's what I'll tell you. I'm totally down to do it. But we have to go over to the other channel, because that's the rule that I have. Is KSP only happens on the other channel. Can we do one thing? Listen, don't leave. Don't leave. Because we have to look at one thing really, really quick. All right, check it. I wanted to show this on the stream, and now I will do it. Hold on, stand by. So this is the upper stage, right? We've all seen this. We worked with it earlier today. And then if I take this off, drop a like in the chat for every time MATLAB crashes. I'm trying to make something good out of this. All right, here we go. The fairing is coming off. Audio is fine. Audio went out? The audio's fine. Oh man, am I getting memed again? The audio's fine. I'm getting memed again. memed by my own viewers. Can't believe it. All right. So this is the FH upper stage fairing. I have a whole video on fairing testing from about like 9 months ago now. Maybe a little bit less than that. But from last fall, I have a whole video on how this stuff works. If you take the top... Oh, nope, can't see that yet. You're not allowed to look. Don't look at that yet. In here, we've got a couple of things. I just wanted to show the inside of the fairing to show people, what was going on here. This is a Nomex blanket, which means it is, it's not fully fireproof, but it's going to protect the parachute, which is in a little burrito that I've made. It's a Nomex burrito. Inside here is the parachute, big orange chute. This is the same one that was used on Thrusty McThrustface, which you can see back there. So the parachute comes out. The parachute is attached to the upper stage. There are a bunch of pyro charges in there. We've got 3 separate charges. So we have some redundancy, which is pretty good. And then, la creme de la creme, the Tesla Roadster with Starman is in the FH upper stage. Now, it has rubber bands on it right now. I'm going to be taking those off before flight. It's in a checklist. Don't worry, it'll be fine. But the FH upper stage has a little Falcon Heavy with a Tesla Roadster, or it has a little Tesla Roadster in the top of it. The other thing I wanted to show, hold on, let me go get it. Oof. So the Roadster is much better than last time. It was, last time we had a Roadster which was modeled by our good friend Charlie Garcia, who once again, you should go watch his videos on building liquid rocket engines. This is what he sent me. It's it was a CAD model that I terribly 3D printed. You can see it's missing a wheel. It's missing 2 wheels. I then painted very sloppily. I drilled through it, put an eye bolt on there, and strapped a parachute to it. So not very good. And that was this is what flew on the first Falcon Heavy flight. And then this winter, he sent me a bunch of composite material and some hoses for some special projects. And along with it, he sent a little tiny Tesla Roadster. So that's flying. It's the true Hot Wheels version. I'm really excited for it. Yeah, it's going to be good. It's a little bit heavier than this, but it's obviously worth the wait. Yeah, and so that's the FH upper stage. That's what we got going on there. So, hold on 1 second. Stand by. Here's the deal, folks. We're going to simulate the flight, because I said we would. That's what the title of the video is. Model Tuning and Simulation. Oh no, should we... Now I feel bad. Because I didn't actually tune the model and simulate it. Okay, listen. If you're watching this back, if you're watching the VOD, because all these videos get put up, I need you to put some comment in the comment section that expresses that I did really try to simulate it. I'm not just trying to pull one over on everyone to get more views or something like that. I tried, and MATLAB crashed 3 times. So just put one in there so everyone doesn't think it's, I don't know, bad. Yeah. We're going to go play Kerbal Space Program. It's going to be on the other channel. And so let me drop a link to it right now. And wait, but we're not just playing Kerbal Space Program. We are going to simulate the Falcon Heavy flight in KSP. But I just try to put all of the KSP stuff on the other channel, which is youtube.com. Oh, wait, Jared has put one in there. Let's see if that goes to it. I think if I do... Yeah, no, it doesn't want to do it that way. Yeah, Jared put a link into it. I'll click it too, make sure it goes to the right place. You can also go to youtube.com/musicmaker. Hold on. What happened to my chat? Oh, jeez. Okay, hold on, everyone. Stand by. This is a mess. Look, here's the deal. Put it in the chat, head to the other channel, click on the link that Jared put in there. I will put a link in here too. I believe that works. There we go. go to that link. I will be live in about 10 minutes. We'll simulate the Falcon Heavy model flight in Kerbal Space Program. I'll see if I can get it to work. And yeah, that's what's up. Wait, when is CRS-18 launching? Hold on. This is crazy. CRS-18. What time is it launching? Is it soon? Hold on. I just need to make sure I'm not going to, like, intersect with it. Oh, 6. It's 6 p.m.? Oh, I have plenty of time. Okay, great. So that's the plan. Thank you for joining. Go head over to the other channel. We'll simulate the Falcon Heavy model flight in that one. I'll try to get it as accurate as possible with the separatrons and everything. The timing won't be fully accurate, but we're going to do our best. And so that's the plan. Don't go away, or I guess just go away, but go to the other channel, and I'll be live soon. That's what's up. Thanks for joining. Next video should be the Falcon Heavy flight. Okay, goodbye everyone.